Hi everyone, my name is Catalin and I'm going to present Toshiba's speech recognition system for the CHiME 2020 challenge. Before I start, I would like to thank my colleagues from the UK, Japan and China for the joint efforts towards this submission. In this presentation, I'm going to start with a general overview of our final system, then more details will be given concerning the front-end and the back-end components, followed by the experimental results. Finally, some conclusions are drawn. Our system was submitted for track 1, corresponding to the multi-array speech recognition task, where the speaker diarization information is provided. The system is based on conventional acoustic modeling, where phonetic targets are tied to features at the frame level. We use deep neural networks to learn the mapping. In terms of ASR frontend, we have used both unprocessed and enhanced data to train the acoustic model. The acoustic enhancement consisted of multi-channel dereverberation using WPE and guided source operation with or without ASR support. Standard filter bank and excitation-based features were independently or jointly used as acoustic features. 4 distinct acoustic model topologies consisting of a combination of CNN and factorized TDNN layers were used in the final system. Results are presented using both the baseline trigram language model, category A results, as well as rescoring with a neural network language model, category B results. Enhancement strategy for training and test described in our recent study published at ASRU 2019, reference 4, has been expanded for CHiME 6. Array data have been processed using dereverberation enhancement or have been processed using multi-array guided source separation. Unprocessed warn data were included in the training set in both cases. GSS enhancement is a blind source separation method aimed at reducing the effect of speaker overlap. It was initially proposed for CHiME 5 and is included in the baseline system for CHiME 6. Given a multi-channel mixture of reverberated overlap speech, GSS estimates the parameters of a spatial mixture model, which is then used to calculate speaker masks. The masks are then used to perform beamforming. In order to operate, GSS requires speaker diarization information extracted from the transcription's timestamps. GSS enhancement with baseline speaker diarization, vanilla GSS, was proven to be quite effective for improving ASR accuracy. However, significant accuracy gains can be achieved by refining the human annotations using ASR estimated silence regions. In our system, we have used both vanilla GSS and GSS plus ASR. To reduce the computational load of the enhancement component in the baseline recipe, GSS was set by default to work with 12 channels input data. Although using all 24 channels does not improve significantly the word error rate, our experiments have shown that combining the outputs of the test data processed in both ways is useful. Therefore, for our system, we have used both GSS 12 and GSS 24. In terms of acoustic features, we have primarily used 64-dimension MEL filter banks, which relate to the vocal tract characteristic of speakers. Our previous CHiME 4 experiments indicated that combining vocal tract features with information about the glottal source improves ASR accuracy. Therefore, we have explored this avenue for CHiME 6 as well by combining the filter banks with 10-dimensional excitation-based features described in reference 5. Finally, 100-dimension I-vectors have been used to augment the previous features. 4 acoustic model topologies have been chosen to build the final ASR system. They consist of factorized TDNN layers and CNN blocks without or with residual connections. All models were trained in Kali using the lattice-free MMI training criterion. The output block of each system had the structure depicted in the top right corner of the screen. Using these building blocks, the following topologies were constructed. The first acoustic model topology is CNN TDNNF. This topology has 10 CNN layers and 9 TDNNF ones. The second topology is ResNet and consists of 40 layers. The third topology consists of a ResNet block, shown here in green, followed by the 9 TDNF layers from the first topology. In total, it has 49 layers. The fourth topology is very similar with the first one and has not been included in this presentation. As mentioned previously, the training array data have been cleaned up using either WP or GSS. The worn training data have been kept unaltered. Threefold speed perturbation was used for data augmentation, and discriminative training was applied on top of lattice-free MMI trained models. Speaker normalization was also explored using VTLN with warp factors estimated for each speaker, room condition, and session. Finally, during testing, the I vectors were refined using ASR-based voice activity detection. An overview of the components included in the final system is depicted on this slide. The first column shows information about the training data. The second column shows the acoustic model topology, and the number in the parentheses correspond to the total number of layers for that particular topology. The third column refers to the system ID that's going to be used to report results. And the last three columns specify whether discriminative training, VTLN, or two-pass I-vector refinement are activated. Due to time constraints, some components were not tested with all AM topologies. For instance, this one. A TDNN LSTM topology has been used for performing language model rescoring. The model parameters were tuned to achieve a good performance on the dev set of CHiME 6. The perplexity of the model is roughly 140. Performance of individual systems described previously has been assessed using the baseline trigram language model. The enhancement in test was either GSS 12 plus ASR or GSS 24 plus ASR. The accuracy of baseline CHiME 2020 system is also included for comparison reasons. The number in parentheses represents the word error rate on the evaluation set. Please note that the values reported for the baseline CHiME 2020 systems were actually based on the vanilla GSS 12 enhancement. That means there is no ASR information. A significant accuracy improvement compared with the baseline is achieved using systems A or B. Adding discriminative training and VTLN improve the performance even further. Refined test I vectors also improves accuracy slightly. The best accuracy is achieved by the ResNet topology, performing discriminative training and VTLN, that is system K, on this slide. The performance of remaining systems follows a similar trend. Roughly the same performance is achieved using GSS 24 plus ASR test data enhancement, as shown in this table. Combining the lattices of all these systems yields 35.89% and 37.55% word error rate on the dev and eval sets, respectively. Finally, the amount of training data for each model is also provided. It is noteworthy that our models achieve better recognition performance than the baseline, using only a fraction of the training data. Rescoring the results using the TDNN LSTM language model improves the ASR accuracy further, as shown here. Combining the lattices of all systems yields 34.83% and 36.83% word error rate on dev and eval, respectively. The best performing system on the dev set, system K, has also been highlighted. session and room breakdown performance of the final system is shown here. The number in parentheses, in this case, represent the numbers corresponding to the TDNN LSTM language model, while the first number is the number for the trigram language model. Results show that the kitchen condition is quite challenging. That's maybe due to the strong noise present in this environment. So this topic is going to need future attention as a topic. To conclude, our system has exploited variability in training and test data enhancement, has explored several acoustic model topologies, acoustic feature representations, and speaker adaptation. On track 1, we achieved very competitive ASR gains using both the trigram and the neural network-based language models, as shown here. Although the current performance is a significant leap compared with CHiME 5, the takeaway message is that there is still enough room for improvement. And on this slide, I provided some useful references used during the presentation. And with that, I thank you for your attention. And if you have questions, you can contact me using the email address provided.